Hello again and welcome back to this course on discrete mathematics, and today we are going to talk about some more applications of relations, that is PGP and GnuPG. PGP is like a pretty good privacy and GnuPG is like GNU private guard. Let's talk about these two things in a little bit. Actually, these two applications which implements RSA algorithms. In last lecture, we focused on RSA algorithms, and today we are going to see more on this. And let's say RSA algorithm is quite good, but we do have more efficient methods these days or better than RSA algorithms. And PGP and GnuPG is one of those softwares and methods that have been developed for privacy, but it's not the best one as far as many cryptographic researchers is concerned. But anyway, we are going to discuss these two parts and these are related to what we discuss in view of relations. In fact, GnuPG is open source and it's free, and if you like you can learn more about these stuff, and these are good cryptographic tools that you might be interested in. And PGP was first written by Philip Zimmermann, and it became quite popular as well. It seems that US government don't like PGP, and never mind about that. Of course there are a lot of other stuff the certain country prohibit, or they like it or they don't. For example, like China, they have their own system to establish this crypto system. So how to crack PGP? PGP in fact is pretty good privacy, the so-called. Factoring n is not feasible, so thus cracking PGP is done by other means. For example, you can intercept the private key by hacking into the computer, stealing the computer, etc. like the so-called man-in-middle attack. We will talk about this man-in-middle attack in a short time. Basically, what people used to do is that they try to send some messages to your system, whether it's your mobile phone or is your computer. They hope you open their message, and the message usually is quite catchy, so that you are forced, or in fact you are tempted to sign in, or you are tempted to open certain files. And once these files are executed in your system, whether it's a tablet, I mean the digital tablet or machine, I mean digital tablet computers or your personal PCs, then the hackers, they can install certain tools which might be useful for them to hack into your system. Well, there is another way as well. The so-called hacking can be done by means of, in fact, infiltrating your network. That can either be done using either your LAN network that you have in hand, or in fact at times Wi-Fi networks can also be hacked, because at times people don't provide a secure password to these things. And we are going to discuss about the so-called man-in-the-middle attack, and that's quite interesting attack, how people has been doing it recently. Let me briefly explain what a man-in-middle attack, and then let's see this illustration here. So what happens is, say for example you have Alice and Bob, these two characters, and Alice is sending a message to Bob asking for a private key. Then Bob sends this message to Alice, and again Bob is asking Alice for her key. So they are sending a message to one another. So once they authenticate the message, I mean the keys, now they send the actual message. For example, say Alice is sending a message to Bob saying, okay, let's meet in the riverside. And Bob says, it's okay, yes, fine, let's meet at the riverside at 5 o'clock. And they meet. Now everything is fine. The message has been sent securely and the key is handled very well. But what happens is that Alice is there and Bob is there, and all of a sudden you have a person coming in the middle, say for example Dan. So when Alice sends a message to Bob, it first goes to Dan, which means that Dan receives the key from Alice, and then he takes the key and he sends the key to Bob. Then Bob sends the key to Alice, but Dan takes the key first and then it sends to Alice. Now the actual message is sent from Alice. For example, let's meet in the riverside at 5 o'clock. So Dan takes this message and he sent another message to Bob. Say for example, he says, let's meet in the downtown near the shopping mall at 5 o'clock. So what happens now? Say for example, Bob goes to the shopping mall at 5 o'clock and he is get robbed, and Alice is still waiting in the riverside for Bob, thinking that Bob is late. Well, that's one of the real-time scenario. Let's see here how things happens by means of this simple animations here. Okay, so now this person is asking, what is your public key? And here he gives, here is my public key. And what is your public key is asked from this side. The blue person is asking now, and he gets the public key. Now here is the message. The message is sent from yellow to blue. Then again the encrypted message is sent back from blue to yellow. This is the normal communication mode. Now here comes the black guy. This is, in fact, don't be wrong with calling the black. In fact, the color here given is the black one. So there are three persons. One is the yellow, black, and the blue one. So the yellow person sends the key. In fact, he wants to send to the blue person, but the man in the middle, he receives this key and he sends this key to the blue guy, which means that the black guy already has this message, and the message sent back to this blue to yellow, but the man in the middle receives this public key and he sends back the private encrypted key. The same thing happens again. So public key is sent and received back and forth, but the man in the middle is already watching the whole scenario. He is receiving all the keys. Now the actual message is sent from yellow to blue, but the man in the middle, he receives that message. So decrypt with corresponding private keys he has, and re-encrypt the message with the blue's public key. So he actually knows what the actual message is because he can decrypt the encrypted message. Now he sends another message to blue, and then the same thing happens. Like he receives a message from blue and he does the same thing. He decrypts this, he knew what the actual message is, and he sent a wrong message to yellow as well. So that's how the man in the middle works. There are a few more public key encryption methods like modular algorithms can be used. This has been developed by US government, so at times it's not widely trusted, and elliptic curves, that is another mechanism. But these days these quantum computers are getting popular. So when I say a quantum computer, in principle a factor n in reasonable time. Say for example, this would make the RSA an absolute. When I say absolute, I mean that RSA could not stand before the quantum computers, and with quantum computers we can still perform various tasks of encryption algorithms can be developed. It's a relatively new mechanism, but these days many people are working on it, and these days it's getting popular. Since we do have quantum computers these days. So this is like to say, in principle you could program a computer to correctly predict the weather. That's something. When I say correctly, it is correct, and we know that that's not easy. So if you could do that, then in fact with many data that you have in hand, in fact you can also predict the wind flow, or in fact you can predict the water flow in the dam. With all these information, in fact you can do other things. For example, if you know the weather conditions, you can clearly know how to control a windmill, how to control a hydel plant, in other words hydroelectric power plant, how to control a solar power plant. All these renewable energy resources are easily predictable, and you can actually efficiently perform many tasks. Well, we know that IBM created the quantum computers, and we do know that other companies do have these kind of quantum computers, the real things they have in hand, and they call the so-called qubits are used instead of the binary bits that we use for traditional computers, or used for this quantum computers. Coming to the partial ordering, equivalence relation is a relation that is reflexive, symmetric, and transitive. Just to recall what we have done, and the partial ordering or partial order is a relation that is reflexive, anti-symmetry, and transitive. So just recall that anti-symmetry means that if A comma B is an element of R, then B comma A is not an element of R unless B equals A. So thus A comma A is allowed to be in R, but since it is reflexive, all possible A comma A must be in R. So in other words, we could say that A comma A is allowed to be in R is kind of reflexive, but in antisymmetric we should make sure if A comma B is part of R and B comma A is not part of R unless B is equal to A. So a set S with partial ordering R is called partially ordered set or poset. So let us say you can denote this whole stuff of partial ordering set as poset. We refer poset from now on for partially ordered set. So partially ordering examples here. So let us show that greater than or equal to is partial ordered on the set of integers. It is reflexive if A is greater than or equal to A for all A is an element of Z, and it is antisymmetric if A is greater than or equal to B, then only way that B is greater than or equal to A is when B is equal to A. That is the property of antisymmetric. And for transitive, if A is greater than or equal to B and B is greater than or equal to C, then you have A is greater than or equal to C. So note that greater than or equal to is the partially ordered set of integers. So with this thought, we have Z, that is the integers, and greater than or equal to is the partially ordered set of integers. So this is a partially ordered set or poset. Symbols. Let us use some symbols and let us perform some more relational operations. The symbol square is used to represent any relation when discussing partial orders, not just the less than or equal to relations. So we can consider, you can represent say less than or equal to, greater than or equal to, or subset, etc. Any symbols can represent certain relations that we talk about. Say you have A, the square symbol that has been used here, A square symbol B denotes A comma B is an element of R, and the poset is s comma this square. Yes, the symbol square is used to denote a square b, but a is not equal to b. So in that case, if the square symbol represents greater than or equal to, then you could say that square symbol also represents the greater than. Well, the fonts for this lecture we set specifically for square symbols are available on the course website. When I say website, we use this LMS system here. You can have more information about this particular symbols, and the abbreviations used in this course will be available on a file where you can see all their representations. Comparability, the elements a and b of poset s comma this square is called comparable if a square b or b square a. In fact, I am just using the square symbol to represent, it is not the actual mathematical squares. Yeah. So meaning if a comma b is an element of R or b comma a is an element of R, it can't be both, because square is anti-symmetric. So unless b and a is equal, here unless a is equal to b, if either a square b or nor b square a, then a and b are incomparable, because you are using the nor part here, meaning that they are not related to each other. So this definition 2 is in the text, you can see here. If all elements in S are comparable, the relation is at total ordering. Basically we are giving out different terminologies like poset, and you have the previous slides also we saw some comparisons, and here comparability, and now we are talking about the total ordering of things. Comparability examples, let's see. Let square be divides operator, consider this as divides operator. Let's talk about here. In poset of z plus, that is positive integers comma divides by, or integers 3 and 9 comparable. Let's talk about this. Yes, 3 divide by 9, that is we can say yes for that, and or 7 and 5 comparable. Well, you know that you can't divide 7 by 5, so or 5 by 7, so you could say no, they are not comparable. Well, at this point of time you can get some point on what a comparability test means. Thus there are pairs of elements in positive integer that are not comparable. The poset z plus comma divides is a partial order. Let's talk about more about this part. If suppose square be the less than or equal to operator, then you have this poset of the form z plus comma less than or equal to, or the integer 3 and 9 comparable. Now talk about this less than or equal to part. 3 is less than or equal to 9. Yeah, it's true, which means it's comparable. And coming to 7 and 5, well, we know that 5 is less than or equal to 7. Yes, all pairs of elements in z plus are comparable, and the poset would be z plus comma less than or equal to is a total order. As we talk about this order, so total ordered posets, linear order, chains, etc., are some of the AKA that can be used for comparable parts of this poset. A well ordered set is another terminology that I would like to share with you. So well ordered well ordered set of say s comma square is here. A total ordered poset is given. Every non-empty subset of S has at least an element. So every non-empty subset of S has at least element. Say for your example, z comma less than or equal to is a total ordered poset. Every element is comparable to every other element. every element is comparable to every other elements. Say it has no least element. So thus it is not a well ordered set. So the definition of well ordered set, we have to have a totally ordered poset, and every non-empty subset of S has at least element. But in this example we can see here that's not the case. So here is another example, S comma less than or equal to, where S is 1 2 3 4 5. Well, a clear definition of S is given to us with the set of 1 2 3 4 5 is a total ordered poset. Every element is comparable to every other element. It has a least element 1. Thus it is an well ordered set. So with regards to well ordered set, I also encourage you to look at this form and try to create different well ordered set with some of the examples that you could find in the website, I mean LMS, where we deal with a lot of other well ordered sets problems. Lexicographic ordering. Well, consider two poset S comma the square sub 1, T comma square sub 2. So we can order Cartesian product of these poset via lexicographic ordering. Say S1 is an element of S and S2 is an element of S, T1 is an element of T and T2 is an element of T. So S1 comma T1 square S2 comma T2 is either S1 square 1 S2, or you could say S1 equals S2 and T1 square base 2 and T2. So lexicographic ordering is used to order dictionaries. As you can see, lexico or lexicographic means it has to deal with the text information, and that's why it's used for order dictionaries. Let's talk more about this lexicographic ordering. Let S and T be the set of words string as well as a set of strings with spaces. Both the relations are alphabetic sorting. So we will formulate alphabetic sorting later. Thus our post is S comma square and T comma square. So here you have these strings run, noun, to, so on, and set, verb, to, and so on. So run square set and run Cartesian product comes before the set one here. So let's simply skip through this information, as these informations are basic for the lexicographic ordering, and basically the lexicographic ordering will not be part of the actual relations we talk about, but the ordering itself is useful for our understanding on the poset of well ordered set. Let's we can do this with more than two tuples. Tuple is the well ordered pairs actually. So you have 1 2 3 4 5 and the square, when square is less than or equal to 1 2 3. So here consider the two strings A sub 1, A sub 2, A sub 3 till A sub m, and B sub 1, B sub 2, B sub 3 till B sub n. So here follows the formal definition of lexicographic ordering of strings. If m equals n, the strings are equal in length, but that's quite obvious. So we can use this comparison for discussion. For example, you have the set A and set B, and you are using this square for the relations. So example, run square set. If m is not equal to n, then T be the minimum of m and n. So you have the set of two strings A and B. So A is less than B if and only if either of the following is true. For example, this A part square B part. In this you have run square set where T is equal to 3. In that case, you can see that A part is less than the B part, because A part has RUN and the B part has SCTS. So that is why we call M is less than N, or in other words A part is less than the B part. In this part we have run square running, and you can see that is quite different from, in fact that is not equal, in fact that is not less than, in fact run is less than running, yeah, that is true. Okay, coming to this Hasse diagram. Hasse diagram is another property in which we can have finite poset or a poset of ordering things. Say for example you have a form of set in which you have 1, 2, 3, 4, 5, and then you have the other element as less than or equal to. When we know its poset, we can simplify the graph. The basic idea of Hasse diagram is to simplify a graph. Say for example let us say you have a graph which have all the directions in it, and you have loops in it. So what we are going to do is that we use 2-3 steps to make this whole graph a simplified one. First, for example, remove all the loops. Try to remove all the loops in the graph, and second you are going to remove all the loop. Again there is kind of a circuit that creates cycles. Remove all the cycles. Initially you are removing the loops. When I say loops, 1, 2, 3, 4 has a loop in it, and the second part you are removing the cycles it creates, and the third part you are removing the arrows, and this is called the Hasse diagram. We are simplifying this whole graph. Well, this has a wide application in various areas, and well, you will be asked to do some experiments, some examples on how to perform the same tasks. For example, I have some note on this here. Look at these examples, and from these examples could you try to form a Hasse diagram? Well, in this example I have given this steps, like you remove the loops. For example, initially the loops are removed, right, and in this step 3 you can see here in this diagram you can see all things like the arrows as well as the circuits being removed. So this is one of the perfect example of Hasse diagram, but I wish you can also look through some of the problems of Hasse diagrams and try to solve it by yourself. There is a challenge here. Suppose you are given with, say this diagram is given to you, can you go back and develop the original graph given to you? Does it sound like decryption? Well, which means that you should have a form, you should have a method to do that. Well, we are nearing the end of this relations, and basically the lexicographic that we discussed today, I do not want to put that part in your homeworks or in your exams, but the other parts that we have discussed might be useful for you to get familiar with, whether it is a Hasse diagram or other parts of this cryptography. I have given you simple algorithms such as the man in middle attack. Yeah, that is quite useful algorithm, useful algorithm for you to come up with so that you can avoid such attacks. Anyway, we are not going to deep into talking about this how to hack or how to crack the things. Rather, here we just saw the applications of relations, and with this I like to conclude today's discussion here, and I hope you understood much of this part on relations. And before that relations, we talked about functions and sets. Well, everything is somehow related if you could contemplate on the things that you have seen in these lectures. And with this we finish the part of lectures on relations and its applications, and as we move ahead we will talk more about how some of the probabilities and some of the counting mechanisms and algorithms and graph theories that have been used in relation with what we have been discussing. Well, with this I conclude today's lecture and looking forward to see you in the next lecture. Until then, have a good time and goodbye.